Hey guys, I hope you're doing well. I hope you're fine. This is a video for Monday's class, and whilst because it's a little late, I will allow you to complete it on Monday night and not Sunday night if you can't. I highly recommend you watch this on Monday night. Anyway, all right. So last week we learned how to express functions. Express radical functions in radical form, and basically that entailed us finding perfect squares and squaring and whatnot. Yeah. Today's main goal is to graph these radical functions. All right. So how do we graph radical functions? That's the question. Yeah. Well, we can treat them. We can always graph this way. This is the number one way to graph. All right. You look at your function, right? You know this function's domain, right? And remember, the domain is the set of x values. So if you know a function's domain, you can just plug in the values from its domain to get its range. I'm trying to use the lingo from the 4 to help you remember. But really, if I know I have x squared, it's my function, I can plug in a number from the x axis, numbers from the x-axis. I know that f of 1 will be equal to 1 squared, it's going to be 1. F of 2 will be equal to 2 squared, it's going to be 4. F of 3 is going to be equal to 3 squared, it's going to be 9, right? So I know my points are 1, 1. So I got 1. I got 2, 4, right? 2, 4. Yeah, I'm a bit short. Then 3, 2, 4 there. And then I have 3 and 9, right? 3 and 9. 9 is up there, but 3 and 9, right? And then if I go to the negative side, right, I should get the same values, right? Okay, right? And this is a flipped. Anyway, never mind. I think you get the idea here, right? Basically, I can plug in values from my x-axis into my function to get corresponding y values, and then connect them. And once I connect them, I get my function value. That's really how you graph a function at elementary level. All right, we know how to do that. So now, what about radicals? Is there anything different? Not really. I can start from f of 1, right? I can get f of 1 here. So f of 1 going to be equal to square root of 1, just 1. All right. So yeah, f of 1 is 1. Okay. So 1, 1. F of 2, square root of 2 is going to be 1.4 something. But now you see the thing when you graph radicals, right? You get these decimals. And we really don't like the decimals. We don't like those because they're kind of hard to estimate where they are sometimes. But to be honest, you can really put a good guess as to where your decimal value is. However, they are just much easier ways of graphing radicals, right? So what we're going to learn today is how we can take advantage of the properties we know about radicals, right? So if I want to graph a function like f of x equals square root of x, as established, I can just plug in points and graph them. That's true, but that's boring. I'm saying that's boring. What you can use is if you know that this symbol here is a square root, right? So therefore, if I plug in a perfect square for x, right? If I plug in a perfect square for x, I will, and I take its square root, I will not get a decimal. I will get a nice whole number, right? So let's see. What are my perfect squares? 1, 4, 9, 16. They go on. Remember, 1 squared. This is 1. It's how you find them. You just square every number. That's how you find your perfect squares. 5 squared, 25, and so on and so forth, right? I think with the axis here, I can only reach 9. So 6, 7, 8, 9. All right. So now if I want to graph my radical, right, instead of graphing every single point to create it, right, and not my radical, rather, if I want to graph something that's been square rooted, remember the square root is asking a particular question. And that question is, what number can multiply by itself to get the number that's within the square root? For example, if I have square root of 25, right, what number can multiply by itself once, or yeah, by itself to get 25? That's 5, right? If you multiply 5 by itself once, or rather if you multiply 5 by itself, yeah, you're going to have 25. So and that's a square root. So that's really important to know for the previous example, for the next example I'm going to give you. Anyway, so back to this, right? So how can I graph this? Yeah. Oh, I know the perfect squares within my domain here are 1, 4, and 9, right? I just don't have a long enough axis to cover all of them. But, and wait, actually, you want to begin from 0, right? Because, so if you know your f of 0 is just going to be 0. You want to begin from 0 to see your function behavior, right? It's very, very important. So square root of 0 is just 0. So your first point is going to be 0. Your next point is 1, right? 1, 1. If I plug in 1 for x, right? I just get square root of 1, it's going to be 1, right? What if I plug in 4, right? You see, I'm not doing 2 or 3 because 2 and 3 will give me a decimal point. But if I plug in the perfect square, right, 4, I get 2, right? 2 on the y-axis. So my x is 4, 2 is on the y-axis over there. And if I plug in 9, right, square root of 9, I'm going to get 3. Remember, and my function here is f of x equals square root of x. Plug in 9, I get 3. So now I know my function's behavior, right? I can just plot this as such, and boom, all right? I have plotted my function, right? We can use these slick skills to plot our functions, all right? And what's its domain? Well, I'll tell you, this domain is inclusive of 0, right? Inclusive 0. So remember, the domain of a radical really is dependent on the, you have to think about it, right? If I have f of x equals square root of x, what's inside should never, all right? What's inside the radical should never be less than 0, all right? Because if it's less than 0, it becomes negative, and the negative basically creates an imaginary number. But we want to stay in with real numbers. We want our domain in today's class. In algebra 2, our domain is always real, all right? So anyway, so yeah, our domain includes 0, right? So we're gonna have 0 and goes all the way. Think about it. Perfect squares are just gonna keep increasing till we stop. So really, it's till infinity. And just to remind you, you always exclude infinity, right? And our range is pretty much the same, 0 to infinity. I know it may look a bit asymptotic, but it's not an asymptote. It'll keep rising because of the perfect squares will keep rising as well. So yeah. X-intercept 0, y-intercept 0, 1 to 1. Remember horizontal line test? So that's going to be what's it going to be? It's going to be yes, yeah. And then onto what's the codomain, right? If our codomain is all real numbers, then our onto setup is no, as it's not onto, right? Well, is it if our codomain is basically, let's say 0 to infinity, then yes, all right? But it's real, all real numbers, no, not for that function, right? Even, odd, neither. If it's even, I mean, these things you worry about later, but yeah. All right. So what about a function like this, right? 3x, 3x, right? We want to graph this function. We said square root of x is asking the question of what number can I multiply by itself twice, right? Or what number can I multiply by itself to get a particular number, right? So if I have 25, what number can I basically say, what number can I multiply by itself, right? Twice, right? I don't know how to say it in proper grammatical sentences, but I hope you know what I mean. Yeah, but what number can I multiply by itself twice to get that number, right? And then that's how I found the perfect squares are like 5 are just whole numbers. The square root of 25 is a perfect square because it's a... Sorry, 25 is a perfect square because its square root is a whole number. But today, we've also touched it a bit in class, but we're going to learn about perfect cube roots, right? If we have a 3 there, remember, if there's nothing there, you can assume there's a 2. But what if you have a 3, right? Well, if you got a 3, what you can do is, if you got a 3, what you can do, what you're really looking for is what number can I multiply this by 3 times, rather, like what number can I multiply by itself 3 times to get 25, right? In that case, 25 wouldn't be a perfect cube root, right? 25 would not be a perfect cube root. It would not. Not all, there are actually, well, relatively, there are less perfect cube roots than perfect square roots, right? But a good example of a perfect cube root is 8, right? 8. So if I have 8 here, right? What number can I multiply 3 times, right? What number can I multiply by itself 3 times to get 8? 2, 2, and 2, right? 2 times 2 times 2 is going to equal to 8. So the cube root of 8 is 2. And because 2 is a nice number with no decimals, we can say that 8 is a perfect cube root, all right? So how would we graph this function, yeah? Well, of course, we start by 0, right? I get my 0, so f of 0 is going to be equal to 3 square root of 0. It's going to be equal to 0, right? So I got my first point there, 0. And then, is 1 a perfect cube root? Yeah, 1 is a perfect cube root, because if we say 3, 1, cube root of 3, right? Cube root of 3, 1, you're going to have 1 times 1 times 1. So, yeah, I'd say 1 is a perfect cube root. So when I plug in 1 in my function, right? So I'm just gonna write the function here for visual sake. So I plug in 1 here, I get a nice 1, right? No pun intended. So then 2 is not a perfect cube root. 3 is not a perfect cube root. 4, 5, 6 are not perfect cube roots. I have to go all the way to 8 for the next perfect cube root. And that's going to be 2, right? So my points here are 1, I got 1, 1, and 8. So I'm going to have, I'm going to have 6, 7, 8. So minus 6, minus 7, minus 8, right? So here I'm going to have 8 and 2, right? And notice I put the negative numbers there. Why did I do that? Because when you square a number, right? When you square a number, you have a positive number automatically, all right? But what if you cube a number, right? What happens when you cube a number? What if I have negative 2 cubed, right? Well, negative 2 times negative 2 is going to be positive, right? So it's going to be positive 4. Then I'm going to multiply by times negative 2 again. So it's going to be negative 8. Oopsie, that's infinity. Negative 8, right? So something different happens here. Something different happens here. Basically, when we cube a number, it can be it can get negative because you're gonna have a negative times negative in there, right? And then that negatives you're gonna have to multiply. It's gonna sorry, you're gonna have a negative times negative, and then that'll turn positive, and that positive is gonna have to multiply by negative to turn back to negative. So the cube root of a negative number will always be negative. So what's the point of what I'm saying? Well, if I plug in f of minus 1 here, right, I'm basically going to have 3 square root or a cube root of minus 1, right? And then this is going to be minus 1, right? I'm not taking the square root, so I can do this, but, right? And this is why cube roots are different from square roots, right? Same concept, but I can get negative numbers, right? Negative 2, 8, right? And boom, I can graph my function. And there you go. There's our function. All right, the domain, or this one, we can see that it goes from negative infinity to positive infinity. Our range, if I was a very good artist, we could see that this is clearly, I'd say negative infinity to positive infinity. And these are all excluding, right? X-intercept 0, Y-intercept 0, 1 to 1, yes. On to, depends on the codomain and the range, right? And yeah, let's see how it goes. So yeah, the last thing we'll learn today, right, is how to find the domain of a function, right? Well, remember, all right, just for you to remember, this is the radical. So every time I say under the radical, I'm basically saying under the square root. All right. So under the square root. So I'm saying find the domain of this radical function. It's question 5. That's what we're told. So the rule to know here is that the expression. All right, I wrote this down. The expression under the radical should never be less than 0. All right. Why? Because the domain will be undefined when the value of what's under it is less than 0. And what's less than 0? You get negative numbers. All right. And notice here we can't really use negative numbers because we're talking about a square root, right? Because remember, if there's nothing there, there's a 2. So how will I find my domain? I'm gonna write my x minus 1 is x minus 1 should be greater than or equal to 0. All right, and then I solve for my x. And instead of getting x alone, right? I'm gonna say my x values here, right? My x value, I'm gonna have minus 1 there, right? Minus 1. Apologies. This should change symbols when I take it across. Right? So it's going to be 1. Yeah, I'm gonna have 0, and then 1, 2, minus 1, minus 2, right? Positive infinity, negative infinity. If you happy remember this from the 4, right? So we're gonna start from positive 1, right? We're going to include positive 1 and go any number above positive 1. And notice if a number is below positive 1, right? Like let's say if we had 0, like if we have f of 0 here, right? We're gonna get x will be 0, we're gonna have square root of negative 1, which is imaginary. But if we begin from 1, right, we're gonna have 1 minus 1, which is going to be 0, right? So that's really how you do that. All right, that's really how you get through this kind of question. And the rule of thumb, we'll do this more in class. I don't want the video to be too long. basically what's under the radical is what matters. All right, everything outside does not matter. Everything outside does not matter. All right. So anyway, now we need to talk about how to get through questions like these. Yeah. So if I have j of x equals 3x minus 2 minus 1, right? So basically we have to find the x-intercept. What do? Well, we gotta remember that the x-intercept is where y is equal to 0. So j of x is going to be equal to 0. It's going to be equal to 3x minus 2 minus 2. All right, I can take m minus 2 across. I'm going to have positive 2 equals to cube of x minus 2, right? So now what do I do from here? Remember this rule I gave you guys? A equals x over y going to be equal to y over ax, right? So I can rewrite this square root as an exponent here, right? So I'm going to get, and you'll see why shortly, all right? So I'm going to have 2 is going to be equal to x minus 2 to the power 1 over 3, all right? So now we want to isolate the x, right? We want to isolate the x. So that's the goal, right? Because we want to know the value of x. So how am I going to do that? I'm going to raise both sides to the power 3. And why am I doing, and why 3? Because I want to get rid of this 1 over 3 here. And I can use the rule if I have a to the power x to the power y, this is going to be equal to a x times y. That rule always works. So I'm going to have 3 times 1 over 3, which is just going to be 1. Then 2 to the power 3 is going to be 8. So it's going to be equal to 8 equals x minus 2, right, to the power 1, which is just itself, right? So I don't even need to write to the power 1. And then now the 2 can go across. 8 minus 2 equals x. It's going to be equal to, we're going to have x equals 6. And that's how you get through those kinds of questions, right? So, yeah, and that's how you do that. Yeah. All right, guys. I know it's a bit long, but hope you go through. And, yeah, see you in class. Bye.